principle or the proof. Okay. So you'll have a chance to test your knowledge of this on the next homework. I'll give a short problem on it, sort of going through the maximum principle. Particular application of that. So let's talk about, let's see, I've talked about this before. Okay, yeah, so let's talk about a couple more features of the heat equation. In particular, we've talked about existence and uniqueness. Let me talk about sort of closing off well-posedness by looking back at continuous dependence. Okay, so continuous dependence. Okay, the heat equation on initial conditions. Okay, remember this is the third primary condition for well-posedness. So so let's suppose, okay, that U1 and U2 solve the heat equation. And I'm going to write out the heat equation on a bounded domain in this case, one-dimensional bounded domain. Okay, so ddt of U j is equal to k d2 dx squared of uj. On x goes from 0 to L, this would be a bounded 1D domain, t greater than 0. We'll say that uj of x0 is equal to some function gj of x. On x is in 0 to L, and we'll say gj is at least continuous. And then lastly, we'll say on the boundaries, uj of 0t is equal to some function aj of t. Uj of lt is equal to b sub j of t, t greater than 0. And we'll say aj and bj are also continuous. Okay. So this is an initial boundary value problem for the heat equation. Again, most of the solutions methods that we've talked about so far are for unbounded domains, either using just the full real line, or the full Rn, or the half line, I guess. Okay. In the next chapter, we'll talk more about using separation of variables to come up with solutions using infinite series. But here, it's easier to present essentially this continuous dependence result in the case of a bounded domain, because that's the context that we have the maximum principle for now. Okay. Probably next lecture, I'll talk about the maximum principle on unbounded domains. It requires a bit more work. Okay. So, so continuous dependence. Okay. What do we need for continuous dependence? We need that if each of the initial boundary value problems, okay, are very small perturbations of one another, then the solution should be small perturbations of one another. Another way of saying that is that the solution should depend smoothly on initial data and changes in parameters. Okay, so let's suppose that W is the difference between U1 and U2, the two solutions to these two slightly different initial boundary value problems. Okay. Well, then if we take the difference and apply linearity, then W should satisfy our original PD. okay, on x is from 0 to L and t is greater than 0, okay? Secondly, w of x0 should equal g1 minus g2 of x, okay, for x is in 0 to L, and this should be continuous. W of 0t should be the difference between the boundary conditions, okay, and WL of t should be the difference between the rightward boundary conditions, okay? So now in order to get this continuous dependence result, we're going to use the maximum principle, okay? So let's start by fixing some t greater than 0, and we'll take the maximum of xt over xt of w of xt, okay? Well, we know by the max principle that we've already proven that this should be less than or equal to the max over the boundary gamma t of w of xt, okay? And just as a reminder again, right, here's our gamma t, gamma t, gamma t, L0, and then here's our t up here, t, this is x, ut, ut. Okay, just draw all that again, okay? Well, what does this imply? This essentially implies that if I take the norm, okay, of these of this result, okay, then the infinity norm of w, okay, should be bounded from above by the max over the norms, infinity norms, essentially of g1 minus g2, a1 minus a2, and b1 minus b2, okay? Right, because if I just take the norm of both sides of these, right, I should still respect the inequality, okay? In addition, the only way to get a maximum here, right, is either to have it be along this segment of the boundary, this segment of the boundary, and this segment of the boundary, and that's represented by these three terms within this max function, okay? So what this implies is that the ICs and BCs, okay, controls the difference in solutions. It controls, or you could say it bounds, the difference in solutions, okay? So that's all we need for continuous dependence, is some bound on the maximum of our difference between the solutions that depends on the difference between the initial and the boundary conditions, okay? So that shows continuous dependence, right? So what was the approach here? Essentially, we just said, well, you know, take the difference and apply the maximum principle to the difference, okay? For uniqueness, you do something similar, okay? You essentially can take G1 equal to G2, call it G or whatever, A1 equal to A2, call it A, and B1 equal to B2, and call it B, okay? And in that case, what you get is what? Well, if U1 and U2 solve the exact same initial boundary value problem, then the entries in this function are all going to be 0, So what does that mean? That implies that U1 minus U2, its norm is bounded from above by 0, okay? Basically for any t greater than 0. And so this implies that U1 has to be strictly equal to U2, okay? Again, assuming continuity, right, which we have continuity of initial conditions and boundary conditions. So of course we're going to have continuity within the interior of the domain because we always have C infinity solutions on the interior of the domain. Okay, so those are two useful results that we can extract immediately from this maximum principle. Continuous dependence, okay, it's handy to have some inequality at our disposal. The maximum and the minimum principle are useful in that respect. In terms of uniqueness, if we just take the difference between two solutions, they're going to solve this, trivial PDE again, and we can apply the maximum principle to that. We know that along the boundaries of the difference PDEs, the boundaries and the initial conditions are going to be 0. Okay, so both the maximum and the minimum are going to be 0. So the only thing that the solution can be in between is 0. So that implies that the difference is 0 everywhere. So that implies that U1 and U2 are the same. Okay. I think the next topic is looking at Duhamel's principle for the heat equation. I think I'm going to save that for the next lecture and just stop for today. Are there any questions about what we went over for today, or any requests for Friday? I think Friday we can just kind of do an exam review session. So you can shoot me an email or just let me know what you might want me to cover ahead of the exam, since you'll be taking your exam on Monday.
Are we going to have a formula sheet for the exam? Or do we have to memorize all of these?
So I don't give a formula sheet on the exams throughout the semester. You will have a formula sheet on the prelim. But for this upcoming exam,